motivation and introduction is that we described what is the average behavior of the universe, so what we call the background universe. So that's what you find in the literature, background, background universe, or unperturbed universe. So this is the things that we are doing. We're assuming that the universe is homogeneous and isotropic, and that's the background or unperturbed universe. And what we saw last time is that in this case, the metric that describes the universe is very simple. It's what's called the Friedmann-Lemaitre-Robertson-Walker metric, which is just something like this. So this, in principle, the metric can be something very complicated, as we mentioned yesterday. It's described by 10 different functions of space and time. But in this case, that we're talking about the background universe, unperturbed universe, is something very simple, assuming that the universe is homogeneous and isotropic. So this is what we saw last time. And so I'm starting from here. This is the scale factor. Which tells everything about the universe. So everything about the universe is in this scale factor. So it's a very, very simple model at the background level. Okay, so again, I'm assuming that, so this is the Friedmann-Lemaitre-Robertson-Walker metric. And just to remind you that in principle, it could have a curvature. The three-dimensional space could be a spherical space, hyperbolic space, or flat, like a three-dimensional Euclidean space. And observationally, we know that it's very close to flat. So I'm just working with the flat Friedmann-Lemaitre-Robertson-Walker. So this is the flat Friedmann-Lemaitre-Robertson-Walker. Very good. So something I want to emphasize now is that these coordinates, so the coordinates x1, x2, and x3 are what we call the comoving coordinates. And let me explain what this is. So if you have two objects in the universe, and the universe is doing whatever it's doing because of the scale factor, these coordinates do not change. All the changes in physical coordinates is given by this scale factor. Is that clear? That's not clear at all. That's very good.
What you mean by not changing?
Huh?
What you mean with not changing?
The coordinates is not changing. So suppose you're in static space.
Okay.
So this room. And you put two objects here, and just let the objects here.
Okay.
The coordinates don't change, right?
Okay. Okay.
Now, the universe is expanding, or I didn't tell you that, but we know the universe is expanding. So the physical coordinates are changing. The physical distances of the object is changing. But all this change is taken into account by multiplying by this very simple scale factor. So the scale factor means that all the expansion of the universe is taken into account by this function a of t, which is that's why it's called a scaling factor. You're scaling the distances, or the comoving distances, by this factor. Still not clear. So let's suppose I have at t equals 0, two objects that are separated by this distance here. And they have coordinates x1, x2, and x3. And the universe is expanding. So at t equals, I don't know, 1, this guy is bigger. My question is, what are the coordinates x1, x2, and x3 of these objects? They're the same. What changed is that the fact that the separation is bigger because you take this separation and multiply. So this is A of t equals 0, and this is A of t equals 1. So I have to multiply by this factor here. Okay? So all the dynamics of the universe, how things expand with time, is taken into account by this scale factor A. And now this has a very interesting consequence, because we can say, okay, so what is the relation between the physical coordinates and the comoving coordinates? So I will call R physical coordinates. And I just told you that R, these physical coordinates, change with time. But this change in time is just due to the scale factor. So very simple. That's the relation between a physical coordinate and a comoving coordinate. Okay? So now let's suppose I want to compute, the universe expanding, things are actually moving because the universe is expanding. I want to compute what is the velocity of objects in the universe. What do? I take the time derivative of what? Of the physical distance. So the velocity is just the time derivative of the physical distance. And this is just, the only dependence in time is in the scale factor. Yes? Right. So the comoving coordinates are such that in those coordinates, the coordinates of this object is fixed. But the object is not fixed. So the physical coordinates are the real ones. Exactly. So I'm assuming that the only velocity of the object is because of the expansion of the universe. That's the assumption. Any other questions? Sorry if this is a bit, okay, basic, but that's okay. So I can write this, very complicated math. I can write this, so I can write this comoving coordinates as the physical coordinate divided by the scale factor. Right? I didn't know anything. And I call this, so this is actually saying how the expansion of the universe is changing with time. This is called the expansion rate. It's a rate. It has dimensions of 1 over time. So this is the expansion rate of the universe. And this has a special name in cosmology. This is Hubble. So, which is a function of time, it's A dot over A. So this is the expansion rate of the universe. And we're going to use this a lot of times, okay? So if this is the first time you're seeing, this is Hubble. Now, if you're looking at things that are very local, so the expansion rate doesn't change much because it changes with time, but suppose you're looking at local things. You can say that you're looking at, again, at local things, local environment. So this is approximately a constant if you're looking at close environments, very nearby environments. And this is actually is defined as the Hubble constant. So this is, by the way, this is not the Hubble constant, right? This is a function of time. So the Hubble constant that you may have heard is actually this function at t equals today. And today, usually write t0. And this is the Hubble constant. which the notation is h naught. So if you're looking at nearby objects, what you expect is that the velocity of these objects is proportional to the distance of these objects. Have you heard of this before? How is this called? Wrong. It was called Hubble law. And then, I don't remember in what year this was changed, and very rightly so. This is called the Hubble-Lemaitre law, because Lemaitre found this first in 1927. But this is valid only locally. You expect changes in this for two reasons. You expect changes. One is because this is not a constant. If you look at large distances, this will change. But the other is whatever I think you asked. This is only assuming that the object expands with the universe. But it's possible that there's some local motion. And these are called peculiar velocities. So there are changes in this. So this is valid only on average and at very large distances. Okay. But we are deriving this in a more proper way because this is not very rigorous. Very good. So we're going to see this, how to derive this in a more proper way later. So now I want to continue and introduce some other concept, another concept that's very important in cosmology, which is a new way of parameterizing time. So the time coordinate is a coordinate. Being a coordinate, you can redefine the coordinate. Instead of using time, you can use time over 2 or whatever, okay? So there's a very convenient way of reparametrizing time. And I tell you why it is convenient. So this is called conformal time. Believe it or not, there is an order in what I'm saying. So this is number 3. I'm trying to follow. Conformal time. So this is the third topic. This is the first real topic of this lecture. So it is convenient to introduce another variable of time, which is called conformal time. And the conformal time, it depends on the references. Some people use eta, some people use tau, but I use eta. So this is defined the following way, that d eta is a redefinition of time, and you scale up, you divide by the scale factor, A of t. So this is just a definition of conformal time. And we're going to use later on, but I think it's interesting to have it now for the moment. So why is this interesting? Because now, if you write the Friedmann-Lemaitre-Robertson-Walker in conformal time, can you tell me what it is? Oh, let me put the C here, just. Yeah, the interesting, why this is interesting, because you can write the metric, it's just this. It's just a square, the eta square, minus the x square. I hate this metric. Okay, it doesn't matter. So yeah, you're right. So why is this convenient? Because when I do space-time diagrams and I use eta instead of instead of time as we measure in the clock, what happens to light rays? 45 degrees. If this was not eta, the light rays would not be in 45 degrees. Okay? So light rays goes in 45 degrees, and you have and this is a light cone in the past, so we are here, and this is the region that is causally connected to us. Okay? This is 45 degrees. So that's why this conformal time is interesting and is very useful. And also what you can see from this is that the conformal for light, so this is 45 degrees. So for light, the variation in conformal time is the same as variation in comoving coordinates. Okay? Is that clear? For light, this is 0, so this has to be the same. Very good. Are we okay? All right. So now we're going to talk about something that's super important in cosmology, and that's the redshift. So with this, now we can more easily talk about redshift. So let's imagine that we have two galaxies, and you have, let's see, put a galaxy like that. I never know how to draw the galaxy. Let's suppose this is a galaxy. At some time t1, it emits a light ray, and it reaches another galaxy here at time t2. So there's a light ray. So let's suppose there's a light ray that's emitted here, and it comes to this other galaxy and reaches this other galaxy at a time t2. And the distance between these two galaxies in comoving coordinates, it's delta x. So far, so good. So I have a galaxy at this point here emitting some light ray at time t1. This light ray will travel and will reach another galaxy, which is separated by comoving coordinate delta x at time t2. All right, okay. So we can compute what is the conformal time that it takes for this light ray to come from here to here. Conformal time. Interval is delta eta of t1, t2. So this is the conformal time interval between t1 and t2. And this is just the definition of the conformal time. This is the integral from t1 to t2 dt a of t. I'm assuming c equals 1, okay? All right. So far, so good. Now, imagine that a second photon is emitted from this galaxy T1 to T2 after a small time interval. So there is a photon that's emitted at T1, and then there's another photon. So let me write this as this, maybe it's easier. This is supposed to be like a time thing. And after, so this is one photon that's emitted here, and then there's another photon that is emitted here at a time t1. So this is t1, and this is t1 plus a small factor delta t1, a second photon. And then the second photon will reach this galaxy at t2 at a time, so I'm put like this. So this photon here reaches at t2, and this guy here reaches at t2 plus delta t2. So it's a second photon. Now, the conformal time interval for the second photon is delta eta of t1 plus delta t1, t2 plus delta t2, right? Which is just the integral of t1 plus delta t1 to t2 plus delta t2 dt over a of t. So I have two different conformal time intervals. One is for the first photon that is emitted at T1, observed at T2, and the second photon, which is emitted a little bit after T1, delta T1, and is absorbed at T2 plus delta T2. Is this clear? Now, the question for you is the following. Is this guy here, this time interval T1, T2, equal, larger, or smaller than this one? Equal. Very good. So why is it equal? Very good. You guys are good. So this time interval, this conformal time difference is equal because it's equal to the comoving distance, and the comoving distance does not change. That's it. Very good. So now we just massage this. And this I leave you as an exercise, because it's just to massage these limits of integration. And you can show, after massaging these limits of integration, that this very simple equality tells you the following, that the integral from T2 to T2 plus delta T2 of dt over A of t is equal to T1 plus delta T1 plus delta T1 of dt over A of t. Just massaging these integrals, if you equate these two integrals and massage the limits, you see that this is true. You can do it, okay? So what does that mean? It means that for small delta t, it means that delta T2 over A of T2 is equal to delta T1 over A of T1. Okay, just get some, this thing is very, very small. So, so you can approximate this integral by delta T2 over A of T2. And the same thing with the other integral. Now let's imagine that the difference between, let's imagine that I'm emitting light at the top of a electromagnetic peak, let's say. So let's say this is a wave, and I'm emitting light at the top at the top of these waves. So this time interval here is proportional to the wavelength of this wave. The same thing here. This time interval here, delta T2, is proportional to the wavelength that is received. So this is the wavelength that's emitted, and this is the wavelength that is received. And this interval, delta T, is just proportional to the wavelength. So what I can write is that, so delta T2 is the received one. AT2 is when the scale factor when it's received. So I would say that the wavelength of the observer divided, so this is the observer. I'm looking at T2, right? A galaxy far away is emitting light, and I am at the galaxy T2. Is lambda emitted at the scale factor T1. So the scale factor changes with time, so that's the whole thing. So the conclusion is that the wavelength is changed. And it's changed because of the expansion of the universe. So you can write, let me just get the order correct, just to make sure. I can get that the wavelength that I observe divided by my scale factor at my time is lambda emitted. Oh, I'm just repeating that. So let me do this. That lambda observed divided by lambda emitted is A, the scale factor observed, scale factor emitted. Okay? So there's something I'm not sure I mentioned to you, but a notation, a convention that we use is that the scale factor today, did I mention that to you? Is conventionally 1. Did I mention yesterday? Maybe not. So the convention is that the scale factor today, and today is T0, is 1. That's by convention. And we are, the observed are us. We are observing today. So what is the value of A observed? 1. So I just put this 1. And this is the scale factor at the source that is emitting the light. Okay? So I guess I would just say, so when I say A is the scale factor at the source, of the emitting source, because A today is 1. Is that okay? So now we can talk about the following. The wavelength that's emitted is not the same as the wavelength that is received by observers here on Earth. There's a change. So this change, so there's the change in wavelength. So let's say this is the wavelength we'll observe, and this is different from the change from the wavelength that is emitted. And let's say this is divided by the wavelength that is emitted by the source. So this is what we define as redshift, or blue shift. I didn't tell you which sign it is, but this is defined as a shift. So it's the shift in the wavelengths. And the shift in the wavelengths comes because of the expansion of the universe. Okay. So the shift in the wavelength is just lambda observed over lambda emitted minus 1. I just explicitly divided by lambda emitted here in the second term. But lambda observed over lambda emitted is what? 1 over A. So we have a relation between redshift and the scale factor. And that's something we use all the time. Are there any questions about this? So the wavelength is changed because of the expansion of the universe. And there's a relation between the redshift, that's something that's measured, and the wavelength, and the scale factor. So I can write this as A. So just put this 1 over A on the other side. So this is 1 minus Z. So this is 1 over 1 minus Z. 1 over 1 plus Z. Okay? So again, today, which we conventionally say T equals T0, Z equals 1. Z equals 0, sorry. So A equals 1. So what happens to A, for instance, when Z equals 1? What is A? 1/2. So at redshift 1, the size of the universe is half of what is today. Because A of t is basically the size of the universe. And so on and so forth. So there's a relation between the scale factor and the redshift. Now, let's go to measurements. So redshifts are easy to measure. And I put easy in quotation marks because nothing is easy. How do you measure redshifts? Or blue shifts?
Spectroscopy.
Yeah, I take the spectra of light that comes from distant objects, try to identify elements and spectral lines of those elements, look where the lines are, and compare with the lines of the same element in the laboratory, and see if they're shifted or not. Okay, so this is the easy way to measure. So there are shifts in spectral lines of elements. So you see the lights from distant objects, distant galaxies. You measure the spectrum, and you try to see how it compares to the spectrum of an element, of the same element on Earth. And there are two ways of doing this in astronomy. There are two main methods. So one is called spectroscopy, which is exactly what I said. So how do you take the spectrum of a galaxy, for instance? You know how they do it? It's amazing. First, you have to know, you have a telescope, and you collect the light of galaxies, for instance, right? But then you need to know where the galaxies are. And what people do is that they take an optical fiber, put on top of that galaxy, and collect the light of only that galaxy, takes that light to a spectrograph, and measure the spectrum. So that's what people do in some of the experiments. And these are done in, if you look at these very large experiments, the first one that did that was the Sloan Digital Sky Survey, and now DESI does that to the Dark Energy Spectroscopic Instrument that's taking data right now. And they have robots, this guy here, they have robots, 5,000 robots that put fiber optics on top of 5,000 galaxies and collect the light spectrographs and take the spectra. It's truly amazing. It's really, really amazing. So I recommend you to Google DESI, the Dark Energy Spectroscopic Instrument. They have videos of the robots putting the fibers and collecting the light, etc. And there's another method, which is called photometry. And photometry, as the name says, is just to take photos. Take pictures, like the picture I showed yesterday. Then you don't need to know where the galaxies are, because you get pictures of all of them. However, you don't have the spectra. But what you do is that you take pictures with different filters, color filters. So this is a very poor spectroscopy, very poor, because you only have information on some color bands. And with that, you try to reconstruct the redshift. You can do it, but the precision is much smaller than this one, this method. However, you get all the galaxies in the field. You don't have robots, you don't need fiber optics, nothing. And also, you have the shapes of the galaxies, which is another source of information, because the shapes of galaxies can be distorted by the presence of matter due to something called the weak gravitational lensing effect. So, and this photometry method is used by the Dark Energy Survey And now the LSST, we use also this type of technique. Those are the main techniques that are used to measure redshifts of galaxies and make these huge surveys, billions of galaxies. Well, Dark Energy Survey has 300 million galaxies, and LSST will have billions of galaxies with some redshift measures. So it's really incredible. Very good. So now we have different ways of parameterizing time. We can use to see how the universe evolves. So we can use the real time, we can use conformal time, we can use the scale factor, because the scale factor is also a clock. When you go back in the universe, the scale factor decreases. And redshift is also a clock. So when you go back in the universe, the redshift increases, right? So when you're looking at the universe at high redshifts, you're looking way in the past. Way, way in the past. Very good. So right now, what I have done so far is just to tell you some of the kinematics of the universe, about this, how do you characterize how the universe changes. And we talked about conformal time, redshift, scale factor, etc. But now it's time to talk about dynamics. How do we know the way the scale factor changes in the universe, for instance? So now I have to tell you the equations of motion of the universe, right? So this is called dynamics. So before I move to dynamics, are there any questions? Is this old news? I mean, you know everything, or is this useful? I hope it's useful. Okay. So now we talk about dynamics. So what controls the dynamics of the universe? So dynamics in Newtonian physics is this, right? You give the equations of motion, and if you have initial conditions, you know what's going to happen in the future. So we need the equations of motion of the universe. So what are the equations of motion of the universe? It's the theory of relativity. It's Einstein's general relativity. So of course, this is a whole, I have 4 lectures, right? So you can spend your life studying general relativity. So in order to understand how the metric changes, we need to know what is the matter content of the universe. That's what Einstein's equation says. So what are Einstein's equations? Now I'm just going to write things. And to derive those things, it's another semester, more or less, course. So yeah, for now on, I'm writing stuff, but you have to believe me. So the equations are complicated, and I tell you what these things mean. So this is something called the Ricci tensor. This, you know what it is? That's the only thing you know, right, at this point? What it is. It's the metric. And this is called the Ricci scalar. And there's some constant that actually the constant has to be set by requiring that this reproduces Newtonian gravity times something called the energy momentum tensor. So this left-hand side of Einstein's equation is totally determined by geometry, by the metric. Even though the metric appears explicitly here, but you see that this Ricci tensor and the Ricci scalar, they are also determined by the metric. So once you know the metric, you know the left-hand side of this equation. And believe me, you're going to compute this. So this is the geometry side of the equations, which is basically the metric. And this right-hand side is what the source of gravity, right? Which is the distribution of matter and energy in the universe. And this is called the energy momentum tensor. Very good. So where does this come from? I'm just saying 2 words. Where does this come from? From classical mechanics. Do you know where equations of motion come from?
I have a question. Are we not going to take account the cosmological constant?
Sorry?
Are we not going to
Later.
take account the,
Later. Yes, so he's asking whether or not I'm including the cosmological constant. And I will include the cosmological constant later. For the moment, it's not relevant. And actually, I include the cosmological constant on the right-hand side, so it's even more confusing for you. But I tell you how later. So, yes, I didn't tell what G is. Do you know what G is? Yes, Newton constant. Good. It's better to know all these things. So where do you get equations of motion in classical mechanics? Principle of least action. So what do you need? An action. So this complicated equation follows from a not so complicated action. So action is S. So there's some action that gives you the left-hand side, which is called the Einstein-Hilbert action, and then some action that describes the right-hand side, which is what we call matter, which actually also depends on the metric, and also fields in the matter content of the universe. And this very complicated equation comes from a very simple Einstein-Hilbert action. There's a very interesting story why this is called Einstein-Hilbert action. And these are called Einstein's equations. But I won't tell you the story. So this is just an integral. And this just comes from invariance. This is invariant under general transformation of coordinates. So this is amazing. So this simple action plus the action of fields that you know that exist, that gives you the T mu nu, gives you this equation. This is something you learn later, I suppose. Very good. So now let me tell you a little bit more what these symbols are. What's R mu nu, etc. But before doing that, we have to define something. And again, I'm just writing things, so I really apologize for this. So you need to take a whole course in general relativity to see the interpretation of these things. But what comes in the construction of this tensor and this scalar, is something called the Christoffel symbols, or connections, or fine connections. And these are first derivatives in the metric. Or a fine connection sometimes. So those are first derivatives in the metric, and they are given by the following. So the symbol is this. They're not tensors, but they have 3 4-dimensional indices, mu, alpha, and beta. And this is the definition. So I'm just writing things again. And you may find this complicated, but you will compute this for the 3 millimeter Robson-Walker metric. And this is just a shorthand notation for the partial derivative with respect to x. So this is the Christoffel symbol. And from the Christoffel symbol, you can construct the Ricci tensor. So the Ricci tensor is derivatives of the Christoffel symbol. So first, notice these are first derivatives in the metric. So if the metric is constant, guess what? This is 0, right? So Minkowski, this is 0. Friedman, Lemaitre, Robertson, Walker, this is not 0. But there's only because of the time dependence. The spatial dependence, any spatial derivative is 0. Okay, so the Ricci tensor is this. D lambda, gamma lambda, mu nu, minus d nu. So the second derivative in the metric now. Mu lambda lambda. There are 2 more terms. Gamma lambda. You don't have to copy because this is in all books. Gamma rho mu nu minus gamma rho mu lambda gamma lambda nu rho. So this is the Ricci tensor. And guess what is the Ricci scalar? Now you can guess. Yeah, it's the contraction of the Ricci tensor of the metric. That's all there is to it. So those are the ingredients that fixes, these ingredients fix the left-hand side of Einstein's equation. So I will leave as an exercise for you to show that for a flat Friedman, Lemaitre, Robertson, Walker metric, there are only the only components of the Christoffel symbol that are non-zero are these ones. And this is equal to A dot delta ij. So this is the Kronecker delta. And gamma of 0 ij is A dot over A delta ij. Those are the only non-zero components of the Christoffel symbols in the Friedman, Lemaitre, Robertson, Walker metric. C appears A dot. A dot because it's a first derivative in the metric. Now from this, you can compute the Ricci tensor. Okay? Another exercise. Let me just notice that these are, how do you say, automatic manipulations. So there are codes that does this for you. You put in the metric, and the code gives you the Christoffel symbols, the Ricci tensor, the Ricci scalar, and everything. But do it once by hand, because it's very instructive, I guess. And it's very nice because it really simplifies. This thing gets very, very simple. So again, you can compute the components of the Ricci tensor, and the only non-zero components of the Ricci tensor are R00, which is minus 3 A double dot over A. Again, the Ricci is derivative of the Christoffel. The Christoffel is a first derivative. So the Ricci is a second derivative or products of first derivatives. So you expect A dot squared to appear, which it does. So Rij is A double dot over A plus 2 A dot over A square Gij. And in particular, R0I is 0. Now, this is actually isotropy also, if you want. And from this, you can compute, finally, the Ricci scalar. And the Ricci scalar, if you do the math, is just 6 times A double dot over A plus A dot over A squared. So, in this very simple case of a background universe, uniform, homogeneous, isotropic, described by a flat Friedmann-Lemaitre-Robertson-Walker metric, these are the only things you have to consider. Again, everything is determined by the scale factor. First derivatives and second derivatives. Why first and second derivatives? Because second derivative is square. Because you know what R is. It's the second derivative of it has to be a second derivative of the metric, or the first derivative is square. So try to reproduce this. It's a good exercise. So now we have everything we need to characterize the left-hand side of Einstein's equation for this very simple case. So now we need to talk about the right-hand side. How the matter and energy is distributed in the universe. And this is given by the energy momentum tensor. So I'm going to talk about the energy momentum tensor now. But before I do that, are there any questions about this? Yes. 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 So Gij is actually is a factor of A. There's a factor of A here. A square. Yeah. Yes. And then delta Kronecker. Yes. Yes. Right. Any other questions? Because this will give you the dynamics of the universe, right? We're computing the equations of motion of the universe in this very simplified, with this very simplification of a homogeneous and isotropic universe. Okay, I have 5 minutes, which is not much. So I'll be really quick about the energy momentum tensor. So, in general, the energy momentum tensor, T mu nu, is a 4 tensor, so it can be divided into a 0-0 component. T0i, Ti0, Tj, and Tji. And this is a symmetric tensor. So again, how many independent components there should be in the energy momentum tensor? 6. It's a symmetric tensor. So, sorry, 10. It's 10. Sorry, it's 10. I'm making a mistake. So because 4 by 4, so it's 10. So there are 10 independent components. Because a symmetric 4 by 4 matrix. Now, again, for our unperturbed universe, isotropy requires that T0I equals 0, because there's no privileged direction, and Tij must be diagonal. So it's proportional to Gij. And homogeneity says that the proportionality here must be at most a function of time, not of space. So the way to describe this energy momentum tensor, in this case of the unperturbed universe, is to imagine that matter is distributed as a fluid. So you really describe the universe as a perfect fluid. And in the rest frame of this fluid, the energy momentum tensor is very easy to characterize. It's characterized by the energy density and the pressure. So what we do is to use a perfect fluid description in which one has only, is a simplification, one fluid that's homogeneous and isotropic. So the 0, component is given by the energy density of the universe, which can be a function of time, and not of space, because we are assuming that the universe is homogeneous. So this is the energy density of the fluid. And the Tij is related to the pressure of the fluid, pressure P, which can also depend on time, Gij. So again, you see that this is consistent with isotropy and homogeneity of the universe. So you can write this, if you want, in a matrix form. So this would be rho rho a square p, a square p, a square p, because of the Gij. And sometimes it's more convenient to write one index down and one index up, because you get rid of these factors of A. So this is just G nu rho T T rho mu. This is the this is the inverse of the metric. So this is just minus 1 over a square, 1 over a square, 1 over a square. So when you contract this, you get minus rho, P, P, and P. So sometimes it's more convenient to write like this. This is in the rest frame of the fluid. If the fluid is moving with 4 velocity, there's a simple transformation with the 4 velocity that I'm not going to write at this point. So now we have everything we need. So what we're going to do next time is to use this form of the energy momentum tensor, these equations for the Ricci tensor and for the Ricci scalar, and write the Einstein's equations in this situation of the unperturbed universe. So you see that this, so how many differential, again, how many differential equations are here? 10. There are 10 coupled differential equations. So it's not easy to solve. So what we're going to see is that in this very simplified description of the universe, where the universe is unperturbed, homogeneous, and uniform, this 10 equations reduces to 2 equations. Only 2 equations. And we're going to solve these equations. And then see, for instance, how the density changes with time, or with the scale factor, and things like that. How the scale factor changes with times. So we can solve everything for the homogeneous and isotropic universe. Okay? So I think I will stop here, unless I have more time. So should I stop and you ask questions, or should I continue? And yes. So this describes radiation in the universe. This describes matter in the universe. This can even describe the cosmological constant. And I will show you that. Okay? Again, for this situation where matter is uniformly distributed, radiation is uniformly distributed, and the cosmological constant is uniformly distributed. Continue. Good. Thank you. That's very good, because I have lots of stuff to do. So let's continue. Okay, now we can actually compute Einstein's equation. So this is 7. Einstein's equation for flat FLRW. So as I told you, there are only 2 non-zero components of the Ricci tensor, the 0, 0, and ij, but ij is diagonal. So there are two sets of equations I need to compute. I need to compute the equations which have 0, 0 indices. So mu equals 0, nu equals 0, and equation which has ij indices. So let's start with the 0, 0. Okay? So now you help me. So it's r 0, 0 minus 1/2 g 0, 0 r is 8 pi g t 0, 0. Okay? So what is r 0, 0? It's minus 3 a double dot over a minus 1/2. What is g 0, 0? It's minus 1. What is r? Is 6 times a double dot over a plus a dot over a square. So this is the right-hand side, and the left-hand side, and the right-hand side is just 8 pi g t 0, 0, which is rho of t. Right? So this cancels, so this is 3. So what you see is that there's 3 a double dot over a minus 3 a double dot over a. This cancels. So the equation is a dot over a square, 8 pi g over 3 rho of t. So this is an equation that relates, this is, if you remember, this is Hubble square. So this is an equation that relates the expansion rate of the universe with the total amount of the energy density of the universe, rho. And this is called the first Friedmann equation, because it was derived by Friedmann in 1922, I guess. Okay? So let's now do the second equation. Which is the IJ equation. So the IJ equation is Rij minus 1/2 of Gij R equals 8 pi G Tij. Now what's Rij? A double dot over A plus 2 A dot over A square Gij minus 1/2 Gij R, which is 6 A double dot over A plus A dot over A square equals 8 pi G P of T Gij. Okay? So I guess a bit late to do all the math. It's not difficult at all. You just actually, you're going to use the first Friedmann equation to eliminate A dot over A for rho. So in the end, you're going to get an equation involving only A double dot, rho, and P. I can do it. Takes 1 minute or 2, but go ahead, right? Go ahead. So this is A double dot over A, if I'm not mistaken, something like that. So this is an equation for the second derivative of the scale factor. So what is the second derivative of the scale factor? What you can think of this as being the acceleration. And the fact that this is negative tells you that the universe is decelerating. So what sources is rho plus P, and this is decelerating. So this is called second Friedmann equation. So of course we know that the universe, I told you that the universe is accelerating, so I have to explain you why. But, and this is why people thought the universe was decelerating, and it was a big surprise when people found out that the universe was accelerating. So what we're going to do next time is to work with these two equations to find out everything. Except we need one more thing, which I tell you next time, which is a relation between pressure. I can do it now. In order to solve these equations, we'll need a relation between pressure and energy density. And you know in thermodynamics how these things are called? Yeah, so we need an equation of state in order to solve this equation. So we have to assume a fluid with a certain equation of state. So that's the relation between pressure and energy density, which is characterized by a function W, which is the equation of state. So next time, we're going to use this in order to solve these equations and find how the energy density changes with the scale factor for different fluids with different equations of state, for instance. Okay? And also how the scale factor changes with time. So we know everything. After this, we know everything. So we can solve the universe, at least for this background uniform universe. And this is the easy part. The difficult part is to put perturbations on top of it. And this is another 6 months course, which I'm not have the time. So how many of you have seen this before? Okay, so some people. So I hope this was useful for people that have not seen this before. All right, so next time.
Yesterday you said the scale factor doesn't depend on the coordinates because the isotropy of the universe, right?
What I said,
At large scales.
so what I said is that because of isotropy, the metric has some specific form.
Okay.
And if you assume isotropy and homogeneity, the most general metric is the Friedman-Lemaitre-Robertson-Walker metric. That's what I said, which is fixed by the scale factor, which is a function of time.
Okay, but we know that in small scales, the universe is not isotropy. So
Yeah, that's what I said from the very beginning. So this is approximation of very large scales. And I told you that if the universe was completely homogeneous isotropy, we would not be here, right? So we know that. How do we treat this? So we start with this background, and you make perturbations on top of it. If the perturbations are small, you can still solve Einstein's equation and see how these perturbations grow with time. If these perturbations are large, you cannot do it analytically. You have to solve it numerically in a computer.
Okay, thank you.
Don't we need the like the continuity equation for the momentum energy tensor?
Right. So the energy momentum conservation is actually an identity in this. You can take the covariant derivative of both sides of the equation. The left-hand side is identically 0. So you can use the conservation of the covariant conservation of momentum tensor to derive things like that too, the continuity equation, etc. But we were sidestepping this with this very simple approach. So we have exercise to do. So
Okay, so no more questions. Let's thank Rogerio again.
okay.